You gotta get the opportunity.
Okay, so we're going to finish off lesson 1 and then do lesson 2. Sometimes determining whether a graph has symmetry might help you with a sketch. So a function is even if f at x equals negative f at x. So in other words, if you take a function and you replace the x with negative x and simplify, if you get the same as the original function, then we classify that as even. And when a function is even, it's symmetrical about the y-axis. So the simplest example of that would be the graph of y equals x squared. Y equals x squared is a quadratic, opens up vertex at the origin, and the y-axis is the axis of symmetry. If you replace x with negative x, you square negative x, all of it, you get x squared. Okay, so that's the simplest example of an even function. A function is odd if f at negative x equals negative f at x, and we'll see examples of that. And when a function is odd, the graph is symmetrical about the origin, which means you'll have corresponding points the same distance away from the origin directly across, or 180 degrees from the original point. So we're asked to determine whether a function is even, odd, or neither. And it's always done by finding what f at negative x is and then comparing it to the original function. So for this first one, if you replace x with negative x, because the power is even, 6 is an even number, that's going to make the negative in front of the x positive, and you'll get x to the 6th, which means that this function is even. This graph will be similar to the graph of y equals x squared. It's just skinnier. The y values will get larger much quicker, because instead of squaring each x value, you're taking each x value and raising it to the power 6. So it's like it's going to do a vertical stretch. Okay. But for question 2, to find out whether it's even or odd or neither, we replace x with negative x. And negative x all cubed is negative x cubed. And for the second term, when you divide a positive by a negative, you'll get a negative. So we can write it like this. And if you compare that to the original, it's not the same. But if you take out a common factor of negative 1, you'll get x cubed plus 1 over x, which is the same as g at x. So this shows us that g at negative x is equal to negative g at x. So therefore, this graph would be odd. It would be symmetrical about the origin. So again, what does that mean? Even though you can't use a graphing calculator for a quiz or test, we can still see what this graph looks like. So we've got x to the power 3 plus 1 over x, which you could also write as x to the negative 1 if you wanted. Set our windows to their standard settings. And that's what that graph looks like. So corresponding points, one of them would be the minimum of the graph on the right and the maximum on the graph on the left. They'd be corresponding points. They are the same distance away from the origin, 180 degrees apart. If you draw a line between those two, it would pass through the origin, and a line always makes an angle of 180 degrees. But not only would they be 180 degrees apart, but they would also be the same distance away from the origin. And there'd be infinitely many corresponding points that would have the same characteristic. Okay, so that's what that means. Number 3, again, to find out what or whether it's even, odd, or neither, we replace x with negative x. And for the first term, because it's an odd power, that means you're going to be having a negative. That is not the same as what we started with. However, if we take out a common factor of negative 1, then what we get inside the brackets is what we started with. Right? So this shows us that f at negative x is the same as negative f at x. So again, this function would be odd. It would be symmetrical about the origin. Question 4, g at negative x, and you replace x with negative x, and you raise it to an even power. That's going to give you a positive x to the fourth, which is the same as the original. In this case, g at negative x is equal to g at x. So again, this function would be even. This is the graph of negative x to the fourth shifted up 1 unit. Vertex at 0, 1. The axis of symmetry will be the y-axis, so it's symmetrical about the y-axis. And looking at number 5, if we find h at negative x, two times negative x is negative 2x, and when you square negative x, you're going to get positive x squared. So that's not the same as what we started with, and in this case, if you take out a common factor of negative 1, you'll get 2x plus x squared, which is also not what we started with. So this would be neither. It's neither even nor odd. It's not symmetrical about the origin, nor is it symmetrical about the y-axis. Okay, so sometimes we might use that in order to help us sketch graphs. And usually it would be kind of at a last resort if you try different things and nothing seems to be working to help you sketch the graph. Sometimes symmetry will. So the next part we're going to look at is what happens to a function as x approaches 0. So if we start with the graph or the function 1 over x squared, and I'm choosing values of x in that table of values that get closer and closer to 0. You see that the values of f at x, or the values of y, are getting larger and larger. Because what happens is that as x gets smaller and smaller, when you square it, it's going to get even smaller, and 1 divided by a number that gets smaller and smaller will give you an answer that gets larger and larger. So we say as x approaches 0, f at x will approach infinity. So the limit as x approaches 0 of 1 over x squared is infinity. So the line x equals 0 is a vertical asymptote of 1 over x squared. Also note that f is discontinuous at 0. It is a non-permissive value. This type of discontinuity is called an infinite discontinuity. So in general, if f at x is defined on both sides of a number a, then the limit as x approaches a of f at x will equal positive or negative infinity. And there are some different ways that we can see this happen. In the case of that first example, notice that the graph is approaching infinity on both sides of the vertical asymptote x equals a. So we can say in this case the limit as x approaches a of this function is positive infinity, because it's approaching positive infinity on both sides of the asymptote. The second example, it's approaching negative infinity on both sides of the asymptote. So that's the value of the limit. This next one, though, it's only approaching positive infinity from the right. So remember, we can talk about one-sided limits. We've done this before. The limit as x approaches a positive means from the right of a. So that the two-sided limit does not exist for this one, just a one-sided limit. And then the next example, you're approaching a from the left. It's still approaching infinity, but the limit as x approaches a negative, meaning that you're approaching x equals a from the left side. And sometimes a graph will approach positive infinity on one side of the vertical asymptote, negative infinity on the other side. So the two-sided limit will not exist. We can say the limit as x approaches a from the left is negative infinity. The limit as x approaches a from the right is positive infinity. And because they're approaching two different values, the limit as x approaches just a does not exist. So we've seen that before. So this is one tool that you might use in order to help you sketch a graph. So this example says find the limit as x approaches 0 from the right side for 1 over x. So this can be done by a table of values. And then after we do this one, we'll see what happens when x approaches 0 from the left. So if we're approaching 0 from the right, we might start like a number like positive 10, then maybe positive 2, then positive 1, then positive a half, maybe positive a fifth, maybe positive 1/10. We can choose any numbers we want. All we need to be able to do is make sure we know what's happening as x approaches 0 from the right, which means all your values are positive. They're getting closer and closer to 0. So when x equals 10, 1 over x will be 1 over 10. When x equals 2, 1 over x will be 1 over 2. So right now, our values are getting larger. When x equals 1, 1 over 1 is 1, so we're still getting larger. 1 divided by a half is the same as 1 times 2 over 1, right? Dividing by a fraction is the same as multiplying by the reciprocal. So 1 times 2, 1 times 5, and 1 times 10. So we can see then that as x approaches 0 from the right side, the value of y will just keep getting larger and larger. So the value of the limit as x approaches 0 from the right side will be positive infinity. If we did a value like 1 over 100, y would be 100. If we did 1 over 1,000 for x, y would be 1,000. So the y values will just keep getting larger and larger. So now we want to find the limit as x approaches 0 from the left side. So if we're to the left of 0, our numbers have to be negative. So we might do negative 10, negative 2, negative 1. Let's say negative a half, negative a fifth, and negative 1/10. So 1 over negative 10 is negative 1/10. 1 over negative 2 is negative a half. 1 over negative 1 is negative 1. So in this case, our y values are getting smaller. We're getting further away from 0. 1 divided by negative a half is the same as 1 times negative 2 over 1. So that'll be negative 2, negative 5, and negative 10. If we chose negative 1 over 100, we get negative 100. If we chose negative 1 over 1,000, we'd get negative 1,000. So in this case, the limit as x approaches 0 from the left side will be negative infinity. So what this allows us to do, right, we know that the graph has a non-permissive value of 0, which means in this case that the y-axis will be a vertical asymptote, because that is the line x equals 0 and x can't equal 0. It's non-permissive. But what it shows us is that what's happening to the graph as it approaches that asymptote on either side. As we approach 0 from the right side, the values of y get larger and larger. They approach positive infinity. So this curve will go upwards on the right side of that asymptote. But as x approaches 0 from the left, now y is approaching negative infinity. So the graph will go downwards as it gets closer to that asymptote. So that's what this is telling us. What's happening to the graph as it gets closer to the asymptote? That's what this tells us, which, again, is a tool that we could use when we're graphing functions that have vertical asymptotes. We want to know what's happening to the graph as we get closer and closer to that asymptote. So we can do the same thing with this next one. Determine the limit as x approaches 6, which is our non-permissive value. Determine the limit as x approaches 6 of that function. So we could do it the same way that we did the last one, by setting up a table of values. But we can also do this by applying some logic here. So what happens as we approach 6 from the right side? So what's the limit as we approach 6 from the right side of 2 minus 5 over x minus 6 all squared? So we're going to approach 6 from the right side, so our values of x are going to be greater than 6. Okay? So what's going to happen here? Well, as we get closer and closer to 6, the difference between our number and 6, the gap between those two is going to get smaller and smaller. When you square a number that's getting smaller and smaller, it's going to get even more small. So you're going to be dividing 5 by a number that gets smaller and smaller. That's going to give you an answer that gets larger and larger. And then you have to go 2 minus a number that gets larger and larger, which is going to give you negative values. And this is going to approach negative infinity. Right? Will that change if we approach x from the left side of 6? So now the values are going to be less than 6. But we're getting closer and closer to 6. Now, the closer and closer we get to 6, when we go those values minus 6, we're going to get smaller numbers. Or we're going to get negative numbers, but when you square it, it's going to become a positive. But those values are going to get smaller and smaller. As you get closer and closer to 6 from the left, the gap between the number and 6 gets smaller and smaller, which will give you a negative decimal. However, when you square it, it's going to get a positive decimal. And just like before, that decimal is going to get smaller and smaller. So when you go 5 divided by a number that's getting smaller and smaller, your answer is going to get bigger and bigger. It'll approach infinity. And 2 minus a number that gets bigger and bigger will get smaller and smaller. Once again, it will approach negative infinity. So because on both sides of 6 you approach the same value, we can say that in this case then the limit as x approaches just 6 of this function is infinity. Which means for this graph, again in this case our asymptote is at positive 6. That's our non-permissive value. So if we say this is 2, this is 4, that'll be 6 there. That's where our vertical asymptote is, because 6 is our non-permissive value. Now we know on either side of 6, we're going to be approaching negative infinity. And I need to add the negative sign in front of what I just wrote. They both approach negative infinity on either side of 6, so that limit does exist. And that will be the behavior of the graph as it gets close to that asymptote on either side. Again, if you're graphing a rational function, quite often you'll have a vertical asymptote. Remember from 30-1, sometimes there's a point to discontinuity there, not an asymptote. But you still want to know what's happening as the graph approaches that non-permissive value. And so it can be a valuable tool to help you sketch. So again, to find the vertical asymptotes of a rational function, Find the non-permissive values and compute the limits of the function from left to right. And that'll tell you what's happening as you get closer and closer to those asymptotes. So for this example, our vertical asymptotes will be found by factoring the denominator. The factors of that would be x minus 3, x plus 2. And so our non-permissive values here are positive 3 and negative 2. So let's find the limit as x approaches positive 3 from the left. And let's just write of f at x instead of writing out the entire function. All right. So as x approaches positive 3 from the left, so that would be like that would be like 2.5, 2.6, 2.9, 2.99, and so on. The top number is going to approach positive 3 because that's what you're approaching. The bottom number, as you're approaching 3 from the left, again, that might be 2, it might be 2.5, it might be 2.8, 2.9. When you go those numbers minus 3, you're going to approach a small negative number. And that's what I'm going to write here, a small negative. That'll be the first factor. I didn't mean to put something that looked like a 1 there. It's just a small negative. Right? When x is 2.5 and you subtract 3, you're going to get negative 0.5. When x is 2.8 and you subtract 3, you're going to get negative 0.2. When x is 2.9 and you subtract 3, you're going to get negative 0.1. Okay, so that number is just going to get smaller and smaller. And the second factor, as x approaches positive 3 from the left, this value of x plus 2 is going to approach a value of 5. So that's what's going to happen here as we approach 3 from the left. So when you have a small negative, and in fact that's going to approach negative infinity, times 5 is still going to make it get even closer to negative infinity. So the denominator is just going to get smaller and smaller. And when you divide 3 by a number that's getting smaller and smaller, your values will approach negative infinity. Because that bottom number will always be negative. That's where the negative comes from. So that's what's happening on the left side of 3. What about the right side of 3? Again, the top number will approach a value of 3. But now on the bottom, when you use numbers greater than 3 and you subtract 3, those values are going to be positive. The gap will get smaller and smaller, so the difference between them will get smaller and smaller, but it'll be positive. So the first factor will be a small positive, and the second factor, once again, will approach a value of 5. So in this case, it's going to approach positive infinity as we approach 3 from the right side. So the limit as x approaches just 3 does not exist because it approaches different values on either side of 3. But now we have to do the same thing for x approaching negative 2 because that is our second non-permissive value. So first we'll do negative 2 from the left of f at x. So the numerator will approach negative 2. The first factor, x minus 3, will approach negative 5. And when x approaches negative 2 from the left, so that would be negative 1, negative 1.5, negative 1.8, negative 1.9, x plus 2 will be negative. And it'll approach negative infinity. So maybe we could, instead of saying a small negative, we'll say that it approaches negative infinity. So on the bottom, you're going to have a negative number times another negative number, which is a positive, but then it's being divided into a negative number. That's going to approach negative infinity. And when we find the limit as x approaches 2 from the right side of f at x, negative 2, I should say. Again, the top number will approach negative 2. The first factor on the bottom will still approach negative 5. But now we're approaching negative 2 from the left side, or from the right side, I should say. So it might be negative 2.5. Then, no, I did that wrong. It might be negative 1, then negative 1.5, then negative 1.8, then negative 1.9, which is going to make the second factor approach positive infinity, because the values of x are less than 2. But like I said, a number to the right might be negative 1. When you let x equal negative 1 and you add 2, you're going to get a positive value. So this one will approach positive infinity. And so on the bottom, you're going to approach negative infinity. The numbers are going to be negative. And on top, you also have a negative. A negative divided by a negative is a positive. So as you approach negative 2 from the right side, the value of that will approach positive infinity. And once again, because the limit as x approaches negative 2 from the left does not equal the limit as x approaches negative 2 from the right, that limit does not exist. But once again, this tells us what's happening as we get closer and closer to those vertical asymptotes. So I have vertical asymptotes at 3 and negative 2. That's where our vertical asymptotes are, at positive 3 and at negative 2. And now we see what's happening as we approach those asymptotes. Right? From the left of positive 3, it approaches negative infinity. The graph is going to come down like that. To the right of positive 3, it's going to approach positive infinity, like that. From the left of negative 2, it approaches negative infinity. And from the right of positive 2, it approaches positive infinity. So we're finding what happens to the graph as it nears those asymptotes. Which again is helpful to know if you're graphing a rational function with non-permissive values. Okay? All right. So we'll stop there. What you can work on for practice is page 212 to 213, questions 2 and 3. I will post these solutions to Google Classroom so you can check to make sure you're on the right track. Remember, after this chapter, we'll have our next exam that'll cover extreme values and curve sketching. Okay?